Welcome, folks. Talking about advanced applications of integrals. Today we're talking about force due to hydrostatic pressure. So we'll give you an overview and we'll talk about different orientations under which we're going to compute hydrostatic pressure and force, namely horizontal orientation and a vertical orientation. So here's sort of the general idea. Everyone knows if you dive down to the bottom of the pool, you'll feel pressure in your ears, and the more depth you have in the fluid, the more pressure you feel. So our goal is to quantify this. So we'll start off with thinking about a horizontal orientation. Okay, so here we're thinking of submerging a thin plate with a square meters area horizontally. We'll think about the fluid over that plate having some mass density, rho kilograms per cubic meter, and we'll think about this plate being submerged at a depth of d meters. So we'll stylize this plate of area A meters squared that's submerged horizontally as sort of a potato. We can think about the fluid above that having volume A times d cubic meters. Of course, if we know the mass density of that fluid, we can compute the mass of the fluid. It's rho times A times d kilograms. Knowing the mass of the fluid, we can compute the force due to the acceleration of gravity on that fluid. And that force is just m times g. So the mass is rho AD times g, or rho g AD newtons. And of course, pressure is force per unit area. So the pressure is rho GD newtons per square meter. Now, we can do this also in imperial units, and the main difference between using standard units and imperial units is that in imperial units, you usually talk about a weight density of delta pounds per cubic foot. And remember that a pound is a unit of force in those imperial units. So a couple examples. Here's the first one. Let's suppose that we have an aquarium that's 8 meters long, 4 meters wide, and 2 meters high. Fluid with mass density rho kilograms per cubic meter to a depth of 1.5 meters. We'll determine the pressure and the force on the bottom of this aquarium due to the fluid. And here, instead of thinking about the acceleration of gravity taking on the value 9.8 meters per second squared, we're just going to leave it as g. So here's a sketch of our aquarium, 8 meters long, 4 meters wide, and 2 meters high, with fluid to a depth of 1.5 meters. So again, we'll sort of start here by thinking about the area of this bottom of the tank, compute the mass of the water fluid, I guess, above it, the force due to the acceleration of gravity, and then the pressure, which is the force per unit area. So again, the area of the base of the tank is 32 square meters. The volume of the fluid above that base is 32 times 1.5 meters of depth, so 48 cubic meters, multiplied by the mass density of the fluid, rho kilograms per cubic meter, to find the mass of the fluid, 48 rho kilograms. The force due to the acceleration of gravity, of course, is just that mass times the acceleration of gravity. So F equals mg, so 48 rho g newtons. And the pressure on the bottom, therefore, is the force per unit area, or 1.5 rho g newtons per meter squared. Okay, we'll do another example, in this case, having a look at our imperial units. So an aquarium 5 feet long, 2 feet wide, and 3 feet high contains fluid with a weight density delta pounds per square foot to a depth of 2 feet. And again, here we'll determine the pressure and force on the bottom of the tank due to the fluid. Similar idea, just different units. So again, here's our aquarium, 3 by 2 by 5. The area of the bottom is 10 square feet. The volume of the fluid above this is 20 cubic feet. Multiply this 20 cubic feet times the weight density to get the force, 20 delta pounds. Of course, the pressure is the force per unit area, so divide by the area to find that the pressure is exactly 2 delta pounds per square foot. It turns out you don't need the acceleration of gravity, and the reason for that is because, again, pounds is a unit of force in the imperial units. Okay, so let's go ahead and think about vertical orientation. And the idea behind this vertical orientation is that the amount of pressure due to a certain depth might change as we move through a vertical depth of a plate. So we'll sort of use this general strategy, slicing at some depth y sub k, computing the force on a given cross section, sum the forces on the cross section, and then recognizing that sum is a Riemann sum that we can take the limit of as n goes to infinity. And a key to all this business is to set a frame of reference that is set where y equals 0 and just leave it as y equals 0. Okay, let's go ahead and think about that same aquarium we just had, the one that's 5 feet long, 2 feet wide, and 3 feet high. In this case, we're going to assume that it's full of fluid of weight density delta. We'll go ahead and determine the force on one of the smaller ends. And again, in this case, since we have this weight density of delta pounds per cubic foot, we won't need actually the acceleration of gravity. Okay, so here again, it's our aquarium, 2 by 3 by 5. I'm going to think about a slice at some depth in the aquarium y sub k. Now at that depth y sub k, we know that the width of the slice is 2 and the height of the slice is some small amount delta y. That tells us the area. With the area of that slice as 2 times delta y, we know that the pressure on that slice is going to be due to the depth of the water above it. So that's going to be just delta times y sub k. Now, of course, force is pressure times area, right? Pressure is force per unit area. So the force on that slice is just 2 times delta times yk times delta y. Now, we haven't said this explicitly, but we're thinking about dividing up all these different depths from 0 depth to 3 depth into subintervals of equal width delta y, and then looking at the force on each of these. So the entire force should be approximately the sum of those. So here's an approximation of that force. The force F, not F sub k, the force F is approximated by the sum of all of these F sub k's from 1 to n. Of course, as n goes to infinity, that approximation becomes exact. Our y sub k's become y's. Our delta y becomes dy. And our sum becomes an integral, in this case, from 0 to 3, because those are the depths on which we divided up the interval. Of course, this is a quick integral to do, and we end up with 9 delta pounds as the force on the smaller end. Okay, let's do another one where in this case we don't have exactly a constant width. Here the width was constant 2. So let's go ahead and think about the force on this triangular plate that's submerged in a tank as we see below. So this tank has depth of 2 meters, and it doesn't really matter how long it is. And the width of the triangular plate is 6 meters. So just like we did before, we'll go ahead and take a slice at some depth delta y, think about the area of the cross section, think about the pressure due to the depth of water on that slice, and then recognize the resulting Riemann sum. So here's the area of the slice at depth y sub k. It's going to be W sub k delta y. And we can see that the width of that slice changes depending on the depth y sub k. Of course, the pressure on that slice is rho times g times y sub k. And you can imagine that the W sub k can be determined using similar triangles. So here we see that WK over 6 is 2 minus y sub k over 2, which gives us that W sub k is 3 times the quantity 2 minus y sub k. So here's our force. Our force is rho g y sub k times the quantity 3 times 2 minus y sub k again. That comes from the width of the slice at depth y sub k delta y. If you want to approximate the force, add up all these bits of forces, let n go to infinity, and as n goes to infinity, we recognize the Riemann sum here. It's the integral from 0 to 2 of rho gy times the quantity 3 times 2 minus y dy. I won't go through the details of the integral in all of its glory, but at the end of the day, what you end up here with is 4 rho g newtons. So that's the force on this triangular plate. And again, I want to point out here that our integral incorporates two things, right? It incorporates the fact that as y gets bigger, the depth of the fluid gets bigger. And it also incorporates that as y gets bigger, the width of the slice gets closer to 0, right? So those are sort of opposing forces in the computation of this force. Okay, folks, hope you've enjoyed this video on hydrostatic pressure and force. Have a great day, and we'll see you next time. Bye-bye.